Good afternoon, grade 12s. This is the last unit I will cover with you for this week, the last week of school, and it is the organic chemistry unit. Carbon forms a vast number of compounds, some 16 million are known and many millions more are possible. Let your imagination be the only limit here, because carbon forms long chains of atoms. So because of that possibility, you can form polymers, you can form molecules that are very long and can be seen in the body, in the human body, in the form of collagen. Our organic life is based on carbon, with a carbon backbone of proteins, fatty acids, and even carbohydrates. The term organic chemistry actually arose from the mistaken belief that organic compounds could only be formed by living organisms, a theory that was proven wrong, I think, in the 16th century, and also by Pasteur in, I don't know if it was the 19th century. There were still people clinging to the notion that it was only organic substance, or living organisms could produce living beings, but all that was proven that the part about living beings producing living things is true, but what they believed mistakenly was that you could take a bunch of dirty rags, throw them in the corner of a barn somewhere, and after a while you'd start getting mice, or that if you left a piece of meat unattended, after a while you'd have maggots crawling on it, simply because the meat itself gave rise to them. It wasn't that at all, it was because flies would come and lay eggs on the meat. Anyhow, in 1828, Wohler, which I misspelled, there's an L there, converted ammonium cyanate into urea. Now, urea is found in urine. It's what your body uses to excrete excess nitrogen. So when we metabolize proteins, ammonia is produced as a byproduct. Your body converts it into urea, so basically two ammonia groups stuck onto a carbonyl group, and then your kidneys have an easy time filtering it out, concentrating it into urine, and disposing of the excess nitrogen. So scientists believe, wrongly, that only something like a living organism could produce a substance like urea, but Wohler proved them wrong and opened a whole new era of chemistry. Carbon typically forms 4 bonds, and so because it has 4 valence electrons, and depending on hybridization, it forms 3 types of bonds with an accompanying geometry. So we could have, with sp3 hybridization, we get a what you see in most carbon compounds, like say methane. So 2 of them are in the plane, one comes out at you, one goes behind the plane of the board. The other possibility is you have the 4 bonds that range in this way, like in a carbonyl group, that's sp2 hybridized. And you can also have sp hybridized the way you have in a cyano group, where the bond angle is 180 degrees. Here it's about 120, here it's 109.5. This is sp hybridized. This characteristic of carbon gives rise to the 3-dimensionality of organic molecules. And now bond strength increases with increasing number of bonds, and also it also shortens. So if you look at carbon-carbon single bond, carbon-carbon double bond, the carbon-carbon triple bond, the bond lengths are 1.54 angstroms, 1.34 angstroms, and 1.39 angstroms. So bond length is often a good indication of just how many electrons are involved in the bonding process. So longer bonds tend to be weaker, and they're also less reactive because there's less electrons available. If you have more electrons available, there's more possibility for them to interact with other species, and you can get a reaction. It's also a stronger bond though, so even though it's stronger, it is still more reactive, paradoxically. So areas in molecules that contain atoms with large enough electronegativities develop a charge separation, which makes them more susceptible to participation in reactions. These areas are referred to as functional groups. Now, organic chemistry is centered very much on understanding these areas where you get a positive charge and a negative charge forming, which then tend to attract each other, because those areas are where you're going to get chemical reactions. If you can generate a positive charge in one part of a molecule and generate a negative charge in another molecule, you can get those two molecules to be attracted to each other in some way, and if you can get them to collide, as they will in any solution where they're both present, you can get them also to react. And it gives rise to a whole branch of chemistry where you can put things together in solution and have them produce something else. Carbon-carbon and carbon-hydrogen are low polarity, which is why organic molecules typically have a low polarity. Molecules with polar groups tend to be water soluble. So for example, things like glucose, which has a lot of hydroxyl groups in it. Ascorbic acid, which is also known as vitamin C, and methanol are all highly water soluble because they interact very strongly with water. They form hydrogen bonds with water, and so it's easy to dissolve those substances in water. Non-polar molecules, on the other hand, are not soluble in water, but they do dissolve in other non-polar substances. Think of gasoline. If you get oil on your hands, how do you clean the oil off? Well, you can get gasoline, because gasoline is a non-polar substance. If you try to mix gasoline with water, you'll get two layers. The gasoline will be on top, the water will be on the bottom, because the water is denser than most hydrocarbons. Most hydrocarbons, like a gasoline, have a density ranging from around 0.6 to 0.9, so it'll float on water. If you ever get, for example, say if you go motorcycling and you drop your motorcycle in the water with a hot engine, the engine will suck water through its muffler, and the water will get into the engine, and then it'll go down into the crankcase. And then once you open your oil pan, the first thing that's going to come out is water. Once the engine has had time to cool down and all stuff settles down, the water will go straight to the bottom of the oil pan, because water is denser than oil. So the first thing that comes out is just water, straight. I've seen that happen. I've done it to my motorcycle. Don't recommend it. But the two substances will not mix, which is a good thing, and so they'll stratify, and the denser one will go to the bottom of the container. In the case of gasoline, if you spill gasoline on water, it'll form a very thin film on the surface of the water. So there's a saying in organic chemistry, or in chemistry in general, it says like dissolves like. So polar substances will dissolve polar substances, non-polar substances tend to dissolve other non-polar substances. And sometimes you get chemical substances which are bridging the gap between polar and non-polar. That's what soap molecules are like. Soap molecules have a polar head and a non-polar tail. So what they do is they bind with one side to dirt molecules, which tend to be non-polar, and on the other side they interact with the water, so they make oily substances water soluble, so you can wash away the dirt that's sticking to your hand, or the oil, or the grime, or whatever. A surfactant is a molecule, so this is what I'm talking about. A surfactant is a molecule that contains both polar and non-polar sections. The non-polar part is quite long. These structural characteristics are found in soaps, detergents, and even in cell membranes. In your cell membrane, you have phospholipids, where the phospho part is polar, so it dissolves in water, and the lipid part is oil soluble. So if you make the phospholipid a little circle, very often they'll represent it as two little strings that are the oily part, and then the head is the part that's soluble in water. So this is the polar part, and this is the non-polar part. And the cell membrane is arranged in such a way that you get, think of the cell sort of membrane, a bunch of these all lined up, continuing in both directions. And so the inside of the cell membrane is oil soluble, and the outside is water soluble. So any chemical that hits it will, if it's not soluble in both, it won't pass through. And so the cell membrane creates a sort of impermeable, semi-permeable membrane. So some organic substances contain acids in them, like what are called carboxylate groups. Others are basic; they'll contain amines in them. We'll look at that later. Typically, the letter R in organic chemistry means anything that is a long chain or any organic substance. And by the way, when you draw stuff in organic chemistry, you don't draw all the hydrogens and the carbons. So what this really means is you have a carbon here, another carbon, another carbon, another carbon, and another carbon. And usually all the carbons have hydrogens attached to them. If they're a carbon on the inside of a chain, they only got 2 hydrogens. If they're on the end of a chain, they'll have 3 hydrogens to satisfy the fulfillment of the 4 bonds, right? And then this last one might be attached to something, right? So this would be the R group, and it could be of any length or size or shape. And this is a pendant bond, meaning it's attached to something. And then here's the hydrogen atoms. So when you ever see an R group, it could be anything. Hydrocarbons are composed only of carbon and hydrogen, and carbon always only has 4 bonds, unless it's some kind of reactive species like a free radical. But typically, if you want a stable carbon, it's got to have 4 bonds going to it. So you'll see all these possibilities: 4 bonds like this. So you could have a double bond and 2 singles. You could have a triple and a single. You could even have 2 doubles, although that's a rare substance. It's called an alkene, not a very stable substance. These are the common ones. You'll see this a lot. And this is rare. Now, the simplest hydrocarbons, meaning chemicals made of only carbon and hydrogen, are alkanes, alkenes, and alkynes. And what's the difference? Well, let's assume they only have one determinant of that name. So an alkene is something that has a double bond in it. An alkyne has a triple bond in it. And alkanes only have single bonds. So only single bonds for alkane. And they have the general formula CnH2n plus 2. They're called saturated hydrocarbons. They have as much hydrogen associated with the carbon as you can possibly have. If you have one double bond, even just one double bond, the molecule now is called an alkene. And so at least one double bond. And that will have the general formula CnH2n. And then alkynes have at least one triple bond, and then they call it an alkyne. And it will have a formula CnH2n minus 2. That is if it only has one of those bonds. These are unsaturated, these are saturated. If you ever look at the ingredients for certain foods, it'll say unsaturated fatty acids. What they're talking about is fatty acids that have double bonds in them. And you'll also see things like hydrogenated vegetable oil. What are they doing when they hydrogenate vegetable oil? They're turning it into a saturated alkane. They're adding as many hydrogens as the stuff will absorb, so that they can change the property of the food for whatever it is that they want it to achieve. Usually what it does is it changes the melting point of the substance so that it either becomes a liquid or solid, depending on what they want from it. You can also get what are called aromatic hydrocarbons. Aromatic hydrocarbons are containing benzene. So they have the general shape. They have at least one of these molecules in it. A cyclohexane with 3 double bonds in it is actually called benzene. So it's a highly unsaturated molecule, but it's quite stable. You would expect double bonds to be reactive, and they usually are, but in this case, because of delocalization, these double bonds flip around continuously. They actually sometimes draw the molecule this way. They just make a circle in the middle to symbolize that there's 3 double bonds in there, and that they're constantly interconverting there. So the electron, they're called the pi electrons because they're pi bonds. If you remember from chapter 9 when we did Vesper theory, those pi bonds are constantly moving around, so they're not as available for reaction, which makes benzene a relatively non-reactive substance. What do we know about hydrocarbons? Well, They don't dissolve in water. But do dissolve in nonpolar solvents. I used to work as, early on after I graduated, I worked as an HPLC analyst. So it was, HPLC stands for High Performance Liquid Chromatography. So what happens in HPLC is they had these little columns made of stainless steel or some other very durable metal, and they filled them with silica, a very, very fine sand, and on that sand they attached organic hydrocarbons to them, long chained hydrocarbons. So if you can imagine, it's like swimming through the weeds on the molecular level. You know, if you ever go swimming in a lake and when you get close to shore, you could feel those slimy weeds sliding against your legs and they slow you down in the water, and it's kind of a gross feeling. But okay, you can do that on the molecular level with HPLC, and when the molecules go flying through, get pushed through the sand, they slow down when they hit these long chain hydrocarbons, especially if the molecule itself has nonpolar properties. The more nonpolar the molecule is, the more it slows down. So you can get molecules, you can pump a tiny amount of mixture, which might have like a dozen or more chemicals in it, and as it goes through the silica, all the chemicals spread out on the column because they all interact different amounts with the material on the inside of the column, and you could thereby extract and separate complex mixtures to do analysis of it. You can imagine how useful that would be, say if you wanted to analyze a blood sample where you suspected an athlete was using a certain type of steroid. You could inject that same steroid into a sample, see where it comes out of the column. It's called when it elutes. They have a special word for it. When the thing passes through the column and comes out, it's called eluting. And when it elutes out, you note the time, and then you inject a sample of the person's blood that's been extracted to remove all the protein so it doesn't interfere with the column. But then when you get all the chemicals that are left over, and if the person has nandrolone decanoate, which is a steroid, in their blood, you'll see the spike of nandrolone decanoate, and then the person will have a spike at exactly the same spot that will have that same elution time. You know that person is taking nandrolone decanoate because your body doesn't make nandrolone decanoate. It's not a naturally occurring steroid. So that's how they spot cheaters in the Olympics, for instance. Or they don't because, well, never mind. Melting and boiling are different things that melting and boiling points tend to increase as the hydrocarbons increase in length. Due to greater interaction. Resulting from London dispersion forces. So obviously if the molecules are longer, they have a longer length of chain to interact over, and they will thereby have a greater attraction to each other. So you can basically identify most unknown chemicals if you have just 3 identification points. A melting point, a boiling point, and a density very often will be enough to identify an unknown chemical. Obviously there are other things. You can measure refractive index, reactivity. You can do it by colorimetry. Certain chemicals, every chemical has its own sort of distinct fingerprint that it absorbs of light waves. You can do infrared spectroscopy. You can do nuclear magnetic resonance spectroscopy. There are dozens of ways of identifying unknown chemicals, and that whole repertoire is available to modern chemists. Nowadays you have machines where you can just inject a sample and you'll get identification of the unknown substance in very short order. Obviously you have to sort of know what ballpark you're in and what you're looking for, but even just a melting point and a boiling point is very often enough. Think about this. If you wanted to identify a single person out of a school of 1,000 people, you could theoretically probably narrow it down to very few individuals out of the 1,000 if you had two sort of distinguishing features. Imagine if you could say, well, the person I'm looking for has a mole right in the middle of their cheek and they have curly hair. That would narrow it down a whole lot. Now you'd obviously have to choose your criteria carefully so that you can exclude as many of the people that could be confused. So if the person was particularly tall, you'd say, well, it would have to be somebody over 6'4", and they have also a mole on their face. So that would probably narrow it down to one or two people at most in even a school of 1,000 people. So, and if you added 3 or 4 other criteria, or 2 other criteria, so you had 3 or 4 criteria, you would probably get it down to one individual quite easily. So it's the same with chemistry. Chemistry, key ideas that help you identify a chemical are things like the melting point, the boiling point, the density. They're all physical properties. And if that's not enough, you can still get it down to chemical reactivity. And usually that's sufficient to identify your unknown chemical. I remember once I got one in university where they just gave me a little vial of a clear liquid, and that was my job, was to identify what the unknown identity of this chemical was. I opened it, took a sniff, smelled like bananas. I said, oh, it's amyl acetate. So I got it right, but then I had to prove that it was the correct chemical. But that's your nose knows, as they say. Examples of how to represent molecules. So butane can be drawn like that. Butane is the liquid you see in your lighter. It has a boiling point of 0, so it's perfect for application in a plastic lighter that can't withstand a high pressure, but it still generates a little bit of pressure at room temperature. So if you press the button on your lighter, you'll hear it hissing, because the liquid is about 25 degrees above its boiling point at room temperature. But that's perfect for an application as a lighter. If they put propane in the lighter, propane boils at something like -40. The pressure would be a little too much for just a little plastic lighter. You'd have to have a metal one to contain that kind of pressure, so it would automatically increase the expense. And if you put pentane, which is one longer than butane, it wouldn't evaporate at a fast enough rate to sustain making a flame. So butane happens to be just so at the right boiling point, so that its application is perfect as a lighter fluid. Here it is, butane. So you have 4 carbons. You notice that you'll put 3 on the terminal ones, 2 on the central carbons, because they're also connected to 2 carbon atoms at the same time. There's a much better way to represent this. There's other ways, obviously. You can say H3C and then connect it to CH2, connect it to CH2 and then CH3. That's another way of representing it. You can even cut out those lines and just draw it like this. That's also valid. But another way is to just say CH3 and then put a bracket, CH2 taken twice, and then CH3. All these are correct, but my favorite is bond line notation, where I just draw the lines. You don't write the hydrogen atoms. So all 5 of those are representations of butane. 1, 2, 3, 4 carbons. The last one faded out a bit there. Okay, so you don't draw the hydrogens on bond line notation. This is called bond line notation. It is the most efficient way of portraying organic substances, and the easiest. And any trained chemist will recognize. When you're a little kid, if you want to draw a bird, you go like this. Right? When you're drawing seagulls, if you're a little kid, you do this. You say, oh, that's a seagull. A chemist will say that's pentane. Okay? 1, 2, 3, 4, 5. Seagull is pentane. So what do we know about hydrocarbons? Let's learn a little bit about hydrocarbons. Hydrocarbons are floppy because the carbon atoms rotate if they're single bonds. If they're double bonds, they don't rotate, and they're actually frozen in one position or the other. They can be both up, or they can be one up and one down. One's called cis, the other one's called trans. Because all the CC bonds can rotate freely, they're floppy. So the molecules are like wet noodles, really. They're all floppy. Isomers are molecules with identical formulas, but different structures. We'll see an example of that. So, first of all, let's just put the definition of isomers so you know how to spell it. They are molecules with identical formulas but different structures. Okay, and let's give you an example. I'm going to use bond line notation because it's the easiest one. You can have a molecule with the formula C5H12. Okay, but you could draw it three different ways. It has this formula, but it's three completely different chemicals. You could have straight pentane, 1, 2, 3, 4, 5, there's your seagull. You could have 1, 2, 3, 4, and then have another one sticking over here from the middle. That's called 2-methylbutane. And I'll show you how to name all these bad boys in a little while, maybe tomorrow. There's pentane. And the third possibility is you could draw it just like this. That's called 2,2-dimethylpropane. So they're all completely different chemicals. They all have different melting points and boiling points, but they have the same exact formula, a C5H12. So they're isomers. As the number of carbons increases, the number of possible isomers increases as well, and it does so geometrically. It increases dramatically. So C8H18, 8 carbons, you can get 18 isomers. With C10H22, so with 10 carbons, you can get 75 isomers. So you can imagine how it just goes crazy after that. The amount of possibilities. Think about how many words you could make with 3 letters. Right? You could have AAA, you could have AAB, AAC, and so on. You could make a lot of words. It would be 26 letters to the power of 3 different. Some of them would be nonsense words, obviously, but you could make 26 to the power of 3 different words with just 3 letters. Imagine how many different words you could make with 26 letters, and I'm just saying words that are 3 letters long. What if you had words that are 10 letters long? Then the possibilities get out of control pretty quickly. So, before we go into how all the different isomers you can draw and how to name them, let me give you a primer on the 10 alkanes that you really should know about because they are the most basic ones. Okay, how are we doing for time here? Let me see. We're at 28 minutes, so I'll give you 2 more minutes. So here are the alkanes that you should memorize. Number of carbons, name, what else? Bond line notation. I'm going to draw you a bond line notation because I don't want to draw them in the old-fashioned way. It's not enough room anyway. So number of carbons, you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's called meth. Now they always end in ane. Okay, that's when it's an alkane, when it's a saturated alkane, X number of carbons, as many hydrogens as you can attach to it, it's going to have an ane ending. So methane, ethane, propane, 3 carbons, butane is 4 carbons, pentane, hexane, heptane, octane, which is the standard for fuels. 100% octane is considered the sort of 100 octane, right? If you want high octane fuel, 100 octane is pretty well as good as you need for most cars. Rarely do you need higher than 100 octane. Nonane and decane. Bond line notation. Now you're not going to draw methane using bond line notation. You'll have to draw it out. Ethane is just a dash. Propane looks like this. Butane like that. Pentane looks like the seagull. Hexane 1, 2, 3, 4, 5, 6. Heptane is 1, 2, 3, 4, 5, 6, 7. Octane is 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's your representations of all of the first 10 alkanes in bond line rotation. There are alkanes that go up to 100 carbons long, and the longer they get, the higher the melting point, the higher their boiling points, they get viscous. Tar is basically a very long chain alkane. Fuel oil is around C12 to C17. Jet fuel is around that length as well. Okay? The formula. I should give you the formula and then we'll wrap it up for today. Formula is CH4, and you'll see that it follows the format of CnH to the 2n plus 2. Okay? Ethane is going to be C2H6. Propane is C3H8. Butane is C4H10. See, it's all following double the carbon and add 2. That's the formula of your alkane. C5H12, C6H14, C7H16, C8H18, C9H20, and C10H22. Those are the formulas for the first 10 alkanes. If you really want to get a quick primer on what I'm going to do tomorrow, I'm going to start talking about isomers and how to identify them and how to name them. I have a whole thing in nomenclature on nomenclature of organic compounds. If you want to get your mind open to that, start watching some of those videos in the playlist, and we will see you tomorrow.